Picture a comet that weighs as much as a mountain in May, then mysteriously sheds 99% of its mass by December without leaving a trace. Impossible, right? Well, 3i Atlas just did exactly that, and astronomers are scrambling for answers. For 5 months, this interstellar visitor behaved like a massive, inert boulder drifting through space. Then, in late December 2025, it suddenly started accelerating like someone flipped a switch. The new data claims it's tiny, barely a kilometer across. But if that's true, where did trillions of tons of matter disappear to? And why did nobody see it leave? Stay with me, because by the end of this, you'll understand why this paradox is keeping physicists awake at night. You'll want to follow along as this cosmic mystery deepens with each new observation. Hit subscribe, because 3i Atlas is still out there, still defying explanation, and the data keeps coming in. The paradoxes we're unraveling tonight are only the beginning, and you won't want to miss it when the pieces finally start falling into place. Scientists just dropped a bombshell that breaks physics, and nobody wants to talk about what it really means. December 23rd, 2025. That's the date everything changed. A team of astronomers published findings that should have been routine, another data point in the endless catalog of celestial observations. Instead, they detonated a paradox so severe that the implications are still rippling through the scientific community. The object in question is 3i Atlas, an interstellar visitor that's been under intense scrutiny since May of 2025. What they found doesn't just challenge our understanding of this particular comet, it challenges the fundamental coherence of our models. The update itself sounds technical at first. Non-gravitational acceleration has been detected in 3i Atlas. Precise astrometry from ground-based observatories, combined with data from space telescopes, confirmed what had been conspicuously absent for months. The object is accelerating in ways that gravity alone cannot explain. Now, if you're familiar with comets, this might not sound shocking. Comets accelerate all the time. As they approach the sun, frozen gases on their surfaces heat up, vaporize, and jet outward into space. That outgassing creates thrust, a gentle but measurable push that alters the comet's trajectory. It's predictable, it's understood, it's textbook physics. But here's where the story gets strange. 3i Atlas showed absolutely zero measurable non-gravitational acceleration from May through September of 2025. Zero. For 5 full months, hundreds of telescopes tracked this object as it barreled through the inner solar system, and it behaved like a lump of inert rock. No jets, no thrust, no deviation from a purely gravitational path. Then, suddenly, in October, the acceleration began. By December, it was undeniable. The same object that had resisted every attempt to push itself for 5 months was now accelerating like it had switched on an engine. You might think this is just a matter of crossing some thermal threshold. Comets wake up as they get closer to the sun, right? That's true, but the timeline doesn't work. 3i Atlas was already well within the zone where typical comets start outgassing. It had been baked by solar radiation for months. If it was going to behave like a normal comet, it should have started accelerating in June or July, not late October. The fact that it waited so long, and then switched on so abruptly, is the first crack in the story. Now let's talk about what non-gravitational acceleration actually tells us. When you measure how much an object accelerates from outgassing, you're indirectly measuring its mass. A heavy object barely budges when gas jets fire. A light object gets pushed significantly. It's basic Newtonian mechanics. Force equals mass times acceleration. If you know the force, and you measure the acceleration, you can calculate the mass. And that's where the nightmare begins. The level of acceleration detected in 3i Atlas implies a small, lightweight object. We're talking about a nucleus roughly 0.82 to 1, 0.05 kilometers in diameter, based on the new models. That's tiny by comet standards. For comparison, Halley's Comet has a nucleus about 15 kilometers long. Comet Borisov, the previous interstellar visitor, was estimated at around 1 kilometer, so 3i Atlas fitting into that range wouldn't be strange, except for one problem. Earlier estimates, based on brightness and other observational data, suggested this thing was much, much larger. Some models placed it as a multi-kilometer giant, possibly as large as 5 or 6 kilometers across. Let's pause and do the math. If you go from a 5-kilometer diameter to a 1-kilometer diameter, and you assume normal comet density, you're not talking about a small correction. You're talking about a mass reduction of roughly 99%. 99%. That's not measurement uncertainty. That's not error bars. That's an object losing almost its entire mass in the span of a few months. Now, comets do lose mass as they approach the Sunday sublimation happens. Dust gets blown away. But we're talking about grams per second, maybe kilograms per second in extreme cases. To lose 99% of a multi-trillion-ton object in 5 months, you'd need to be hemorrhaging millions of tons per second, continuously, for months. The sky would be filled with debris. We'd see a massive, glowing tail stretching across the solar system. Space telescopes would be tracking an expanding cloud of gas and dust visible from Earth with the naked eye, and we see none of that. The comet's brightness stayed relatively stable. Its coma, the fuzzy envelope of gas and dust around the nucleus, didn't explode into some supernova-level event. Photometrically, it just looked like a normal, slightly active comet. So here's the contradiction we're stuck with. If 3I Atlas is small enough to accelerate the way it does now, it must be light. But if it was that light all along, why didn't it accelerate in May, June, July, August, or September? And if it was heavy enough to resist acceleration for 5 months, where did 99% of its mass go without leaving a trace? This isn't a comet misbehaving. This is physics failing to describe the same object in 2 consecutive time windows. It's like watching a freight train roll down the tracks for months, utterly indifferent to the wind, and then suddenly watching it lift off the rails and glide like a paper airplane, using the exact same fuel. You can't have it both ways. Either the train was always light and we missed something fundamental, or the train lost most of its mass in a way that defies every observation we made. The distinction matters because this isn't some distant, abstract object. 3I Atlas was tracked by NASA, the European Space Agency, and hundreds of independent observatories. The data is real. The measurements are precise. This is not a rumor, not a fringe theory, not a misidentified asteroid. This is an object under the most intense scientific scrutiny we can bring to bear. And it's giving us 2 mutually incompatible realities. So what changed between September and December? Did the object transform, or did our understanding collapse? If 99% of the mass vanished, where's the body? Let's get quantitative, because the paradox only gets worse when you run the numbers. Early estimates of 3I Atlas, based on its brightness and assumptions about how much sunlight it reflects, place the nucleus at several kilometers in diameter. Brightness doesn't directly tell you size, but if you assume a typical comet's surface reflectivity, somewhere around 4%, you can back-calculate an approximate diameter. Those early models suggested something big. Not a planet killer, but substantial. A multi-kilometer chunk of ice and rock, dense enough to remain inert under solar heating for months. Then came the December 23rd update. The new analysis, incorporating the non-gravitational acceleration data, tells a completely different story. The nucleus is now estimated at 0.82 to 1.05 kilometers in diameter. That's a reduction by a factor of roughly 5 in linear dimensions. But volume scales with the cube of the radius, so a 5 times reduction in diameter means a 125 times reduction in volume. Assuming similar density, that translates to a mass reduction of about 99%. Let's put that in perspective. If the original mass estimate was on the order of 10 trillion tons, the new estimate is closer to 100 billion tons. That's a difference of roughly 10 trillion tons of material that either never existed or disappeared without a trace. 10 trillion tons. That's equivalent to a mountain range evaporating into space in 5 months. Now, let's be fair. Comet size estimation is notoriously difficult. The nucleus is often obscured by a thick coma of gas and dust, especially when the comet is active. Brightness measurements can be misleading if the coma is much larger or brighter than expected. It's entirely possible that the early estimates were wrong from the start. Maybe the object was always small, and we just miscalculated because we couldn't see the nucleus clearly through all the surrounding haze. But even the most generous reinterpretation of the data doesn't fully close the gap. Yes, coma can inflate brightness estimates. Yes, assumptions about reflectivity can be wrong, but we're not talking about a 20% error here. We're talking about a factor of 100 in mass. Even if you assume the coma was unusually bright, even if you adjust for every possible observational bias, you still can't reconcile the object's inert behavior in the early months with its dramatic acceleration later on. Here's why. If the object was always small and light, then the same outgassing forces that are pushing it now should have pushed it just as hard in June. The sun was already heating the surface. Water ice, carbon dioxide ice, and other volatiles should have been sublimating. Jets should have been firing. Acceleration should have been measurable, but it wasn't. For 5 months, 3I Atlas moved like a dead rock. No measurable deviation from a purely gravitational trajectory. That behavior is consistent with a massive, inert object, but the December acceleration is consistent with a tiny, lightweight object. Same object, two incompatible descriptions. Let's debunk the obvious escape route. Maybe the comet just lost a lot of mass naturally. Comets do that. As they approach the sun, they shed material. Maybe 3I Atlas had an unusually violent outburst that stripped away most of its mass in a short period. Problem is, we'd see it. Mass loss on that scale produces observable phenomena. Dust clouds, gas emissions, brightness spikes, changes in tail structure. We have centuries of comet observations to draw on, and we know what catastrophic fragmentation looks like. Comets have split apart before. We've watched it happen. And it's always dramatic, always visible, always leaves evidence. 3I Atlas left no such evidence. Its brightness stayed stable. Its coma didn't explode. There was no reported debris cloud expanding into space. No sudden brightening event. No fragmentation signature. Photometrically, it looked like business as usual. So if 99% of the mass disappeared, it did so in a way that left almost no trace. That's not how physics works. There's another angle to this. If the mass loss was gradual and continuous, spread out over months, you'd expect to see a gradual increase in non-gravitational acceleration as the object got lighter. Imagine a rocket burning fuel. As the fuel depletes, the same thrust produces more and more acceleration because there's less mass to push. If 3I Atlas was steadily losing mass from May to December, we should have seen a smooth ramp-up in acceleration. Instead, we got nothing for 5 months, then a sudden switch. It's not a gradient. It's a binary state change. So we're left with two broad possibilities. Either the mass was never as large as we thought, and something fundamental about our measurement methods is broken, or the mass actually changed in a way that our models can't explain. The first option is uncomfortable because it means our brightest-based size estimates, used for decades across thousands of comets, might be systematically wrong in ways we don't understand. The second option is worse because it implies physics we haven't accounted for. Let me offer an analogy. Imagine you're watching an ocean liner cross the Atlantic. For 5 months, it moves slowly, steadily, indifferent to wind and waves, exactly as you'd expect from a massive ship. Then, suddenly, it starts moving like a speedboat, accelerating rapidly, carving sharp turns, responding to every gust of wind. And when you look at it, the wake hasn't changed. The waterline hasn't shifted. There's no evidence the ship got smaller or lighter, but its behavior says it must have. That's 3I Atlas. The scientific community is scrambling to reconcile this, and the explanations are getting creative. When your comet starts defying Newton, you invent new geometry. Scientists hate paradoxes, not because they're inconvenient, but because they expose gaps in understanding. And when faced with a paradox, the first instinct is to find a way to preserve the existing framework. That's what's happening now with 3I Atlas. A flurry of hypotheses have emerged, all attempting to explain the contradiction without invoking exotic physics. The leading contender is what I'm calling stealth physics, the idea that the acceleration was always there, but we just couldn't see it. Here's how it works. Imagine the comet is outgassing, just like any normal comet, but the jets are oriented in such a way that they cancel each other out from our perspective. Maybe there are two jets firing in opposite directions. From Earth, we see no net acceleration because the forces balance. Or maybe the comet is rotating, and the jets are positioned symmetrically around the rotation axis, so the thrust averages to 0 over time. In either case, the comet could be accelerating locally, moment by moment, but when you integrate over days or weeks, the net effect is invisible. This hypothesis has the advantage of preserving normal comet physics. No need to invoke mysterious mass loss or exotic mechanisms, just geometry and bad luck. If the jets happened to be aligned in a way that made them invisible to us, and then something changed, maybe the rotation axis tilted, maybe one jet shut off, then suddenly we'd see the acceleration that was there all along. It's not a crazy idea. Comets are chaotic. Their rotation is unpredictable. Jets can turn on and off as new patches of ice get exposed to sunlight. Asymmetric outgassing is common. In fact, there's some evidence that 3I Atlas might have exhibited unusual jet behavior. Reports from mid-December noted a wobbling anti-tail jet, a rare feature where gas appears to stream toward the sun instead of away from it. Anti-tail jets are optical illusions caused by geometry, but they indicate complex, asymmetric outgassing patterns. So maybe, just maybe, the comet's jets were perfectly balanced for months, canceling out any net thrust, and then in October, something shifted. A new vent opened. The rotation axis wobbled, the balance broke, and suddenly, we could see the acceleration. But here's the problem. This explanation requires a stack of coincidences. First, the jets have to be oriented in exactly the right configuration to cancel from our line of sight. Second, that configuration has to remain stable for 5 full months, despite the chaotic nature of comet activity. Third, the change has to happen suddenly and dramatically enough to produce the observed acceleration in December. And fourth, this all has to occur in a way that leaves no other observable signature, no brightness changes, no coma asymmetries, nothing that would tip us off to what's happening. Each of those conditions individually is plausible, but all of them together? That starts to feel like the universe is playing a trick on us. Astronomers call this the Feynman luck problem, named after physicist Richard Feynman's quip that unlikely events happen all the time if you look at enough cases. But 3I Atlas isn't one case among thousands. It's the only active interstellar comet we've studied in detail since Borisov in 2019. And Borisov didn't pull this trick. It behaved exactly as expected from day one. So yes, stealth physics is possible. But it requires us to believe that we just happened to catch this comet during a 5-month window when its jets were perfectly balanced, and we just happened to be observing from the exact angle where the cancellation was complete, and the balance just happened to break right when we were still watching. It's not impossible, it's just improbable. And there's another wrinkle. If the jets were firing symmetrically for months, where was the coma? Outgassing produces visible gas and dust. Even if the thrust cancels out, the material itself should still be detectable. We should have seen an active coma from day one, even if the acceleration was hidden. But early observations described 3I Atlas as relatively inactive. It wasn't dead, but it wasn't gushing either. The coma grew as the comet approached the sun, which is normal, but there was no indication of massive, hidden outgassing in May or June. Still, the hypothesis has traction because it fits within known physics. It doesn't require us to rewrite textbooks or invoke new forces. It just asks us to accept a very specific, very unlikely geometric arrangement. And for many scientists, that's preferable to the alternative, which is admitting we don't understand what's happening. But not everyone is buying it. Some researchers are looking at the timeline more carefully and asking a different question. What if the issue isn't geometry? What if it's timing? What if the comet wasn't hiding its thrust? What if it just hadn't turned on yet? There's another class of explanations that focus less on where the jets were pointing and more on when they started firing. This is the thermal lag hypothesis, and it's rooted in the physics of heat conduction. The idea is simple. When a comet approaches the sun, the surface heats up quickly, but the interior takes time to warm. Heat has to conduct inward through layers of ice, rock, and dust. Depending on the composition and structure of the nucleus, that process can take weeks or even months. So maybe the acceleration we're seeing now isn't from surface ice sublimating. Maybe it's from deeper layers, reservoirs of volatile ices that didn't start vaporizing until the heat finally penetrated far enough. In this model, the comet was inert for 5 months because the internal volatiles were still frozen. Then, sometime in October, the temperature gradient reached a critical threshold. Deep ice started sublimating. Pressure built up beneath the surface. Jets formed and broke through. Acceleration began. This hypothesis explains the timing. It gives you a mechanism for why the comet stayed quiet for months and then suddenly woke up. And it's consistent with some of the observational data. Spectroscopic analysis of 3I Atlas detected carbon dioxide in the coma, which is interesting because carbon dioxide ice sublimates at a lower temperature than water ice. If the comet has a CO2-rich interior, That could be a sign that deeper, colder layers are now outgassing. But thermal lag alone doesn't solve the paradox. Yes, it explains when the acceleration started, but it doesn't explain how much. The magnitude of the observed acceleration still implies a small, lightweight object. If the comet was massive enough to resist acceleration for 5 months, then even delayed outgassing shouldn't produce the dramatic thrust we're seeing. You'd need an enormous amount of gas venting at incredible rates to push a multi-kilometer, trillion-ton object. And again, we'd see evidence of that. The coma would be massive. The brightness would spike. The tail would stretch across the sky. None of that happened. The comet's activity level increased, yes, but not to an extent that suggests catastrophic, high-volume outgassing. It looks like a normal, moderately active comet, which brings us back to the mass problem. If the acceleration is real, and the activity level is moderate, then the object must be small and light. But if it's small and light, why did it act heavy for so long? There's one more twist to the thermal lag story. Most comet models assume a standard density around 0.5 grams per cubic centimeter. That's the typical value for a fluffy, porous mixture of ice and rock. But what if 3I Atlas isn't typical? What if its density is higher, or its structure is more complex? A denser object could behave differently under the same thermal conditions. It could resist heating longer. It could store more internal energy. It could release gas in bursts, rather than steadily. But now we're stacking hypotheses. We're saying maybe it has delayed activation, and maybe it has unusual composition, and maybe it has a layered structure. Each maybe is plausible on its own, but together they start to feel like we're building a custom explanation to fit one object. That's not science, that's storytelling. And yet, the alternative is even more uncomfortable. Because if thermal lag doesn't fully explain it, and stealth physics doesn't fully explain it, then we're left with the possibility that something fundamental about our models is wrong. Maybe the way we estimate comet masses is broken. Maybe the way we interpret brightness data is flawed. Maybe the assumptions we've relied on for decades are systematically biased in ways we never noticed because we never had an object like this to test them. 3I Atlas isn't just a puzzle, it's a stress test. Change one number, rewrite the entire story. Let's talk about density, because it's the silent variable that determines everything. When you see a bright object in space, you measure its brightness. You estimate its size based on assumptions about reflectivity, and then you calculate its mass based on assumptions about density. Every step involves assumptions, and the final number, the mass, is only as good as those assumptions. It's a chain of inference, each link depending on the one before it. Pull on any single assumption, and the whole chain shifts. Change the density, and you change the mass. Change the mass, and you change the entire physical story of what this object is and how it behaves. For comets, the standard assumption is that the nucleus is a fluffy, porous mix of ice, rock, and dust, with a density somewhere around 0.5 grams per cubic centimeter. That's half the density of water. Think about that for a moment. These objects are less dense than the liquid in your glass. They're cosmic snowballs, loosely packed aggregates held together by weak gravity and the cold of space. It's based on decades of observations, spacecraft flybys, and laboratory studies of cometary material. We've sent probes to comets. We've watched them up close. We've measured their composition, photographed their surfaces, analyzed the dust they shed. The 0.5 grams per cubic centimeter value isn't a guess. It's grounded in real data. It works, most of the time. But 3I Atlas is forcing us to ask whether that assumption holds. What if this object is denser than we think? What if it's not a fluffy snowball, but something more compact, maybe even metal-rich? If the density is higher, then the same size nucleus would have more mass. And a more massive object could resist acceleration longer, even if it's physically small. Suddenly, the paradox starts to crack. Not completely, not cleanly, but enough to suggest we might be looking at this the wrong way. This isn't pure speculation. We have some hints from spectroscopy. Early observations of 3I Atlas detected nickel and cyanide compounds in the coma, which are unusual but not unheard of in comets. Most comets are dominated by water ice, carbon monoxide, carbon dioxide, and simple organic molecules. Nickel is rarer. It's not impossible. Plenty of comets show trace metals, but it's notable. Nickel, in particular, suggests the presence of metal-rich dust or possibly even metallic fragments embedded in the ice. If the nucleus has a higher than average metal content, its density could be significantly higher than 0.5 grams per cubic centimeter, maybe closer to 1 or even 2 grams per cubic centimeter, maybe even higher if there are concentrated pockets of denser material. Doubling the density doesn't fully solve the paradox, but it changes the math. A 1-kilometer nucleus with double the standard density would have twice the mass of a typical comet the same size. That means more resistance to acceleration. It means the object could stay inert longer under the same thermal conditions. The sun heats the surface, but a denser, more massive object has more thermal inertia. It takes longer to warm through. It takes more energy to trigger significant outgassing. And when outgassing does start, it takes more force to produce measurable acceleration because there's more mass to push. It also means the observed acceleration in December would require stronger outgassing to produce the same effect. You can't push a heavy object as easily as a light one. If 3I Atlas is denser than assumed, then the outgassing we're detecting must be more vigorous, more energetic than it appears. But here's where it gets tricky. Spectroscopy tells us about the composition of the gas and dust in the coma, not the composition of the nucleus itself. We're seeing what's being ejected, not what's still inside. It's like trying to figure out what's in a package by examining the wrapping paper. You get clues, sure, but you don't see the contents directly. The coma is a cloud of vaporized ice, liberated dust, and fragmented particles blown off the surface. It represents the outermost layers of the nucleus, the stuff that's been exposed to sunlight and heated enough to escape. But the interior? That's hidden. That's a black box. We infer its properties, but we don't observe them directly. It's entirely possible that the nucleus has a layered structure. Maybe the outer layers are normal, low-density ice, the kind we expect from typical comets. But beneath that, maybe there's a denser core. Rock, metal, concentrated volatiles, compressed over billions of years. As the outer layers sublimate away, exposing deeper material, the average density of the active surface could change. What we're seeing in the coma today might not reflect what the nucleus looked like in May. The object could be peeling back layers, revealing a different composition as it approaches the Sunday. That would explain the behavioral shift. Early on, we were seeing a low-density surface that didn't outgas much. Later, we're seeing a transition zone, or maybe the beginning of a denser interior that behaves differently. Or maybe there are pockets of high-density rock embedded in a low-density ice matrix. Imagine a sponge, mostly air and soft material, but with hard nodules scattered throughout. The sponge is light overall, but the nodules are heavy. If the nodules are concentrated in certain areas, the density isn't uniform. Some regions are fluffy, others are dense. Heat penetrates differently. Outgassing happens asymmetrically. The object's response to solar heating becomes patchy, unpredictable, dependent on which regions are currently active. That could produce the kind of erratic behavior we're seeing. Months of quiet, then sudden acceleration as a dense pocket finally heats through and releases trapped volatiles. Or maybe the whole thing is hollow, with a thick shell and a void in the center. Hollow comets aren't unheard of. Fragmentation, internal cavities left by ancient outgassing, structural voids created during formation, all of these are possible. A hollow object has less mass than a solid one, but it also has strange thermal properties. The shell heats faster because there's less material to conduct through. But if the shell is thick enough, it might still resist outgassing until the temperature builds up internally. And once outgassing starts, the dynamics are different. Gas venting from a hollow cavity could produce more erratic, pulsing jets rather than steady emission. That fits some of the observations. The wobbling anti-tail jet reported in December could be evidence of internal pressure variations, gas escaping through cracks or vents in an irregular shell. Each of these structural variations would produce different thermal, mechanical, and dynamical behaviors. A hollow comet would heat up faster, but hold less mass. A layered comet could show delayed activation as heat penetrates to deeper, denser layers. A metal-rich comet could resist fragmentation and produce unusual spectral signatures. The possibilities multiply once you abandon the simplifying assumption of uniform density. And that's both liberating and terrifying. Liberating because it gives you more tools to explain the observations. Terrifying because it means you've lost the anchor of certainty. you're no longer working with a single, well-defined model. You're juggling a dozen competing scenarios, each plausible, none definitive. And that's the problem. Science relies on simplifying assumptions to make predictions. You can't model everything. You can't account for every possible variation. So you make reasonable assumptions based on past experience, and you build models that capture the essential physics while ignoring the messy details. It works brilliantly when the objects you're studying are similar to the ones you've studied before. But when you encounter something genuinely different, something that doesn't conform to your expectations, the simplifying assumptions become liabilities. They blind you to possibilities. They force the data into a framework it doesn't fit. But when the predictions fail, you have to decide which assumptions to discard, and that's agonizing. Do you abandon the density assumption, the reflectivity assumption, the composition assumption? Each one is backed by decades of research. Each one has worked for hundreds of other objects. Discarding any of them feels reckless, but keeping all of them forces you into paradoxes. You're damned either way. Changing the density assumption rewrites the entire narrative of 3I Atlas. It changes the mass estimates. It changes the thermal models. It changes the predictions for future behavior. And it opens the door to a much wider range of possible explanations, some of which veer uncomfortably close to speculation. That's why some scientists avoid this path. It's not that the idea is wrong. It's not that higher density is implausible or contradicts the data. It's that once you start questioning foundational assumptions, the model becomes less predictive and more descriptive. You lose the ability to make confident statements. You can explain anything after the fact by tweaking the density here, adjusting the structure there, adding a layer of complexity to match the observations. But you can't predict what will happen next. You trade precision for flexibility. And in a field that prides itself on rigorous quantification, that's a hard pill to swallow. Astronomy is built on predictions. We calculate orbits decades in advance. We forecast eclipses centuries into the future. We pride ourselves on mathematical rigor and empirical verification. Admitting that we don't know the density, that we can't pin down the structure, that we're guessing at fundamental properties, feels like failure. But the data isn't giving us a choice. 3I Atlas is behaving in ways that don't fit the standard model. The numbers don't add up. The timeline doesn't make sense. The observations contradict the predictions. Either we adjust the model, or we admit the model is incomplete. There's no third option. And adjusting the model means rethinking density, structure, and composition in ways that might apply to other interstellar objects we haven't studied yet. This isn't just about one comet. It's about the framework we use to understand all of them. If our density assumptions are wrong for 3I Atlas, how many other objects have we mischaracterized? How many comets have we cataloged with incorrect masses because we assumed 0.5 grams per cubic centimeter? How many asteroids are actually denser or lighter than we think? The implications ripple outward. If density varies more than we've accounted for, then our models of solar system formation need revision. If interstellar objects have compositions we haven't encountered, then our understanding of planet building around other stars is incomplete. If layered structures are common, then our thermal models for comet activity are oversimplified. One anomaly, one weird comet, and suddenly the whole edifice of planetary science is wobbling. That's both exciting and unsettling. Exciting because it means there's still so much to learn, still fundamental questions we haven't answered. Unsettling because it reveals how much we've taken for granted. We thought we understood comets. We thought density was a solved problem, and maybe for solar system comets, it mostly is. But 3I Atlas came from somewhere else. It formed under different conditions. It spent billions of years in environments we can't replicate. And it's teaching us, loudly and insistently, that our models need work. So, maybe density is the key. Maybe it's not. But either way, the question is now on the table, and it's not going away. The universe has a habit of breaking finish theories. 3I Atlas isn't alone. Over the past few years, astronomy has been confronting a growing list of observations that don't fit neatly into existing models. It's not that the models are wrong, exactly. It's that they're incomplete. And every new anomaly exposes another edge case, where our understanding falters. What we're witnessing isn't a crisis in science. It's something more subtle and more profound. We're watching the slow accumulation of evidence that our frameworks, however elegant and predictive they've been, are starting to show their seams. Take the James Webb Space Telescope discoveries in 2023 and 2024. JWST has been finding galaxies in the early universe that are far too massive and well-formed to exist according to standard cosmological models. Galaxies that should have taken billions of years to assemble are showing up fully mature just a few 100 million years after the Big Bang. It's not a contradiction, but it's a tension. It means something about our models of galaxy formation is missing a critical piece. The galaxies are there. They're real. We can photograph them, measure their spectra, count their stars. But according to everything we thought we knew about how structure forms in the universe, they shouldn't exist yet. They arrived at the party too early, already dressed and sophisticated, when they should still be getting ready. The immediate response from cosmologists was predictable. Maybe the mass estimates are wrong. Maybe we're misinterpreting the redshift data. Maybe there are feedback mechanisms in early star formation that we haven't accounted for. Each explanation is plausible on its own, but collectively, they represent a scramble to preserve the existing framework rather than confront the possibility that something fundamental might be missing. That's not dishonesty. That's how science works. You exhaust every conservative explanation before you start rewriting textbooks. But the longer the tension persists, the harder it becomes to ignore. Or consider the recent magnetar observations. Magnetars are neutron stars with insanely powerful magnetic fields, and they occasionally emit bursts of X-rays and gamma rays. These objects are already at the edge of known physics. They're stellar corpses crushed down to city-sized spheres, spinning at incredible speeds, wrapped in magnetic fields a quadrillion times stronger than Earth's. We barely understand them under normal conditions. In 2024, astronomers detected a magnetar that was flaring in a pattern that didn't match any theoretical prediction. The bursts were too regular, too intense, and too long-lasting. Models struggled to account for the energy budget. The magnetic field would have to be sustained at levels that should cause the crust to crack, the interior to convect differently, or the whole star to behave in ways we've never observed. Some researchers proposed exotic mechanisms involving quantum effects in the magnetosphere. Others suggested the object might not be a pure magnetar at all, but some hybrid state we haven't categorized yet. Maybe it's transitioning between rotational states. Maybe it's accreting material from an unseen companion. Maybe there are plasma instabilities, creating feedback loops we don't have equations for. The explanations multiplied, each one adding a new layer of complexity, because the simple models just didn't work. These aren't crackpot fringe theories. These are mainstream scientists grappling with data that doesn't conform to expectations. And the pattern is the same every time. The initial observations seem fine. The models predict certain behaviors. Then new data comes in, higher resolution, more precise, and suddenly the models don't work anymore. The response is always the same. Scramble to adjust parameters, propose new mechanisms, add epicycles to the equations. It's not that the scientists are being stubborn or dogmatic. It's that the existing framework has been so successful for so long that abandoning it prematurely would be reckless. But at some point, the patchwork becomes harder to defend than a clean admission of ignorance. 3I Atlas fits this pattern perfectly. It was supposed to be a straightforward interstellar comet, measure its size, track its trajectory, analyze its composition, file it away in the catalog, but the data refused to cooperate. The mass estimates didn't match the acceleration. The timeline didn't match the thermal models. The behavior didn't match the predictions. And now we're left with the same kind of patchwork explanations we see in cosmology, astrophysics, and planetary science. Every proposed solution requires a specific set of conditions. Every hypothesis adds another variable. The simple story: a comet from another star passing through our system has fractured into a dozen competing narratives, none of which fully explain what we're seeing. The public often sees these anomalies as hints of something revolutionary, some breakthrough discovery that will overturn everything we know. There's a hunger for paradigm shifts, for moments when the old guard is proven wrong and a new understanding emerges. It makes for compelling stories: the lone genius challenging orthodoxy, the anomaly that changed everything. But that's not how science actually progresses most of the time. Scientists, meanwhile, tend to downplay anomalies, emphasizing that the existing models are mostly right and just need refinement. They point out that the standard model of particle physics has been confirmed to astonishing precision. General relativity works brilliantly for everything from GPS satellites to black hole mergers. Newtonian mechanics still gets rockets to Mars. The models aren't broken, they're just incomplete. Both perspectives miss the point. Anomalies aren't revolutions, they're stress tests. They reveal where our models are strong and where they're weak. And in aggregate, they tell us something important about the limits of current theory. A single anomaly might be noise, a measurement error, an instrumental artifact. But when multiple independent anomalies start accumulating across different fields, all pointing in the same general direction, toward models that work beautifully in familiar regimes but falter at the edges, that's a signal. It's a signal that we're probing new territory, and the maps we brought might not be detailed enough. What's striking about the current moment in science is how many of these stress tests are happening simultaneously. JWST is challenging cosmology. Gravitational wave detectors are finding black hole mergers that shouldn't exist. Pairs of massive black holes colliding in environments where formation pathways are murky. Particle physics is seeing hints of new forces in muon decay experiments, tiny deviations from predicted values that could indicate physics beyond the standard model. Neutrino oscillations keep revealing surprises. Dark matter remains stubbornly undetected despite decades of increasingly sensitive experiments. Dark energy is still a placeholder name for something we don't understand. And now, 3i Atlas is challenging our understanding of cometary dynamics. Each field is facing its own version of the same question. Are these isolated quirks, or are they symptoms of a deeper gap in our framework? Are we dealing with 1,000 unrelated puzzles, or are we circling around a smaller number of underlying issues that manifest differently in different contexts? Nobody knows yet. The data isn't clear enough. The theories aren't developed enough. But the fact that the question is even being asked is significant. I'm not suggesting there's some grand, unified answer. I'm not invoking paradigm shifts or scientific revolutions. But I am saying that when multiple independent lines of evidence all point toward incomplete models, it's worth paying attention. 3i Atlas might be a fluke, a statistical outlier, a measurement error that will be corrected in the next round of observations. Or it might be the canary in the coal mine, warning us that the assumptions we've relied on for decades are starting to crack under scrutiny. We won't know which until we have more data, but dismissing it prematurely would be a mistake. And here's the thing. We're only going to see more of this. Telescopes are getting better. The Square Kilometer Array is coming online, which will probe the radio universe with unprecedented sensitivity. The Vera Rubin Observatory will survey the entire southern sky every few nights, discovering thousands of transients and variables. NASA's Nancy Grace Roman Space Telescope will map the cosmos in infrared, searching for dark matter and distant galaxies. Data is getting more precise. Observations are probing regimes we've never accessed before. Every new mission, every new instrument, every new survey is going to surface more edge cases, more anomalies, more paradoxes, objects that don't quite fit, phenomena that resist easy explanation, contradictions that demand resolution. That's not a bug, that's science working as intended. The whole point of better instruments is to test our theories more rigorously. If all we ever found was perfect confirmation of existing predictions, we'd stop learning. Anomalies are where the learning happens. They're uncomfortable, yes. They create uncertainty. They force scientists to admit ignorance. But they're also the raw material of progress. Every major advance in physics started with something that didn't make sense. The orbit of Mercury, the ultraviolet catastrophe, the photoelectric effect, galaxy rotation curves. Each one looked like a minor puzzle at first. Each one eventually required a fundamental rethinking of the framework. We're not there yet with 3i Atlas. We might never be. It might turn out to be exactly what the conservative explanations say it is, a comet with unusual geometry and unlucky timing. But it does mean we're entering a period where certainty is harder to come by. Where every press release has to include more caveats. Where models have to carry more asterisks. That's uncomfortable for scientists who are used to speaking with authority. It's uncomfortable for the public, who want clear answers. But it's also honest. And in the long run, honesty about uncertainty is more valuable than false confidence. Which brings us to the real question. What if the object isn't the problem? What if our categories are? Let's revisit the central paradox one more time, because it deserves to be stated clearly. 3i Atlas behaved like a massive, inert object for 5 months. Then it behaved like a small, lightweight object in December. We have two incompatible descriptions of the same thing, and no clean way to reconcile them. Every explanation we've explored, stealth physics, thermal lag, density variations, requires us to believe in a very specific, very unlikely set of conditions. And even then, the explanations only partially work. They patch one hole while opening another. They solve the timing problem, but not the mass problem. They explain the acceleration, but not the earlier silence. We're playing whack-a-mole with contradictions, and the mallet keeps missing. So maybe we're asking the wrong question. Maybe the issue isn't what 3i Atlas is. Maybe it's how we're categorizing it in the first place. Maybe the paradox exists not in the object, but in the framework we're using to interpret it. Think about the language we use. Comet, asteroid, interstellar object. These are human labels, imposed on nature for convenience. We draw boundaries based on composition, behavior, origin. If it's icy and outgasses, it's a comet. If it's rocky and inert, it's an asteroid. If it came from outside the solar system, it's an ISO. Simple, clean, categorical. But nature doesn't care about our categories. Nature doesn't organize itself into neat taxonomic boxes with clear boundaries and mutually exclusive properties. Objects exist on a continuum. Some are icy, some are rocky, some are somewhere in between. Some outgas, some don't, some do it sporadically. Some come from the Oort cloud, some from the Kuiper belt, some from other star systems. And some, like 3i Atlas, seem to blur every boundary we've drawn. 3i Atlas crosses all these boundaries. It's interstellar, so it's an ISO. It shows cometary activity, so it's a comet. But it behaved like an asteroid for months. Its composition includes both ice and possibly metal. Its structure might be layered, porous, or fragmented. It doesn't fit neatly into any single box. And maybe that's the point. Maybe it's revealing that our boxes are too rigid. Maybe the universe is trying to tell us that the categories we've relied on for centuries are useful approximations. But approximations nonetheless. They work most of the time, for most objects, in most situations. But push them hard enough, probe them carefully enough, and they start to fail. This isn't just a philosophical quibble, it has practical consequences. When we classify an object as a comet, we apply certain models. We assume certain densities, certain compositions, certain behaviors. Those assumptions guide our predictions and our interpretations. We plug the object into equations designed for comets, and we expect comet-like results. But if the object doesn't actually fit the category cleanly, then the models break down. We end up with paradoxes like the one we're facing now, not because the object is behaving strangely, but because we're forcing it into a framework it doesn't belong in. It's like trying to describe a platypus using only the categories of mammals and birds. You can force it into one or the other, but you'll always end up with contradictions. The platypus isn't broken. The categories are incomplete. Now imagine scaling this up. We've only studied 3 interstellar objects in detail. Oumuamua, Borisov, and now 3i Atlas. 3 data points. That's not a sample size. That's barely a hint. That's not even enough to draw a trend line. And already, we're seeing behaviors that challenge our models. Oumuamua accelerated without visible outgassing, defying every explanation we threw at it until someone proposed it might be a hydrogen iceberg, which is exotic but at least physically plausible. Borisov looked like a normal comet, familiar and reassuring, but came from an alien star system with unknown formation conditions. 3i Atlas is pulling this mass-switching trick that breaks the internal consistency of our observations. 3 objects, 3 different puzzles, 3 ways of refusing to conform. What happens when we find 100 interstellar objects? 1,000? The Legacy Survey of Space and Time, launching soon, will catalog millions of moving objects. Some fraction of those will be interstellar. What if the categories we've built from solar system objects, comets, asteroids, Kuiper belt objects, don't apply cleanly to visitors from other systems? What if interstellar space produces objects with compositions and structures we've never encountered? We're assuming that the physics is universal, and it is. Gravity works the same everywhere. Thermodynamics doesn't change across star systems. But the specific outcomes of that physics depend on local conditions. Different star systems, different protoplanetary disks, different formation environments. A comet that formed around a metal-rich star might have a completely different composition than one that formed in our solar system. An object that spent billions of years drifting through the interstellar medium, bombarded by cosmic rays, might have a surface chemistry we've never seen. There's no reason to expect interstellar objects to neatly mirror our own. This is where machine learning and AI might actually help. Human brains are good at pattern recognition, but we're also good at imposing false patterns. We see categories where there are only gradients. We draw lines where nature has only transitions. We impose order because disorder makes us uncomfortable. AI, trained on large datasets, might identify clusters and correlations that don't align with our intuitive labels. Maybe there are natural groupings of objects based on behavior, composition, and structure that cut across our existing taxonomy. Maybe 3i Atlas belongs to a category we haven't named yet. Maybe there's a cluster of interstellar objects with layered structures and time-dependent activity that we'll only recognize once we have enough examples. Machine learning doesn't care about historical categories. It finds patterns in the data itself. That could be liberating, or it could be disorienting. Probably both. But that raises an ethical question. How much uncertainty should scientists communicate to the public? Right now, the messaging around 3i Atlas is cautious. Most press releases emphasize that it's a comet, that the acceleration is understood in principle, that the data is still being analyzed. The paradoxes are downplayed, the ambiguities are softened. Language is carefully chosen to project confidence and control. That's partly because scientists don't want to fuel speculation. They've seen what happens when preliminary findings get sensationalized. Headlines that scream about alien artifacts and physics-defying objects. Comment sections filled with conspiracy theories and pseudoscience. The instinct is to batten down the hatches, emphasize normalcy, and wait until the dust settles before admitting how confused everyone actually is. But it's also because admitting deep uncertainty feels like admitting failure. Science is supposed to provide answers. That's the social contract. The public funds, research, and scientists deliver understanding. Saying we don't know feels like breaking that contract. It feels like incompetence, like the experts aren't living up to their title. So the tendency is to overstate certainty, to present working hypotheses as settled conclusions, to imply that the remaining questions are minor details rather than fundamental gaps. But uncertainty isn't failure, it's honesty. And in cases like this, where the data genuinely doesn't fit the models, being upfront about the gaps is more valuable than pretending we have answers we don't. The public can handle complexity. What they can't handle is being misled or condescended to. People are smart enough to understand that science is a process, not a finished product. They can grasp that some questions take time to answer, that some observations require years of follow-up, that some paradoxes resist easy resolution. What erodes trust is the slow realization that scientists were downplaying uncertainty to maintain an image of authority. That breeds cynicism. That creates the exact conditions for misinformation to flourish. And the truth is, 3i Atlas is confusing the experts. That's worth saying out loud. The people who study comets for a living, who've spent decades modeling these objects, who can recite the orbital parameters of famous comets from memory, are genuinely puzzled by this thing. That's not a scandal. That's not a failure. That's what happens when nature surprises you. And communicating that surprise, that genuine scientific bewilderment, might actually be more engaging than false confidence. So here's the real question we're avoiding. What if 3i Atlas isn't the anomaly? What if our models are? What if the frameworks we've built over centuries of astronomy are powerful, useful, but ultimately provisional? What if every new observation, every new instrument, every new discovery is pushing us toward a more complete understanding, but also revealing how much we still don't know? That's not a comfortable thought. It means the map we've been using has blank spaces we didn't know existed. It means the territory is larger and stranger than we thought. This isn't defeatism. It's humility. And humility, in science, is often the precursor to breakthroughs. The paradoxes we can't explain today become the textbook examples of tomorrow, once someone figures out the missing piece. Look at the history. The precession of Mercury's orbit was a paradox until general relativity explained it. The photoelectric effect was a paradox until quantum mechanics resolved it. Galaxy rotation curves were a paradox until dark matter, or modified gravity, or something we still don't fully understand, entered the picture. The paradoxes aren't obstacles, they're signposts. They mark the edges of current theory and point toward what's next. Maybe 3i Atlas will be one of those examples. Maybe it's already teaching us something we're just not ready to hear yet. Maybe in 20 years, students will read about it in textbooks as the comet that forced astronomers to rethink their classification schemes, or their density models, or their assumptions about interstellar formation. Or maybe it'll turn out to be a statistical fluke, an outlier that doesn't generalize, a curiosity that gets footnoted but doesn't reshape the field. We won't know until we have more data. But dismissing it prematurely, forcing it into categories it resists, would be a mistake. One day, we'll look back on this moment and wonder why we were so confused. We'll see the missing piece clearly, and it'll seem obvious in retrospect. Or maybe we'll look back and realize this was the moment we started asking better questions. The moment we stopped trying to force nature into our categories and started listening to what nature was trying to tell us. Either way, 3i Atlas isn't going away. It's out there, accelerating through space, indifferent to our models, indifferent to our categories, doing exactly what it was always going to do. And we're left here, watching, measuring, trying to make sense of an object that refuses to make sense. Maybe that's the real lesson. The universe doesn't owe us coherence. It doesn't organize itself for our convenience. It just is. And our job is to keep watching, keep measuring, and keep questioning, even when the answers don't come easy. Especially when the answers don't come easy, because the easy answers are usually the ones we already know. The hard answers are the ones that push us forward. 3i Atlas is a hard answer, and we're still working on the question.